Okay, here is part 2 of the summary over the chapter discussing solutions. We left off on part 1 talking about when you form a solution, there is interaction between the solute and the solvent. Well, when you take a solute and dissolve it, you have to break apart the intermolecular forces, the intermolecular attractions that exist in the solute. You have to do the same with the solvent. And then the solute and solvent will interact and dissolve and become miscible. Well, that involves 3 energy changes in this whole process. So whenever you form a solution, we can measure what's called the heats of solution. The heats of solution are typically found by measuring the actual temperature change that occurs between the starting temperature of the solute solvent and its final temperature. Okay, and so heats of solution can be measured as exothermic or endothermic. Exothermic heats of solutions are those that involve typically an increase in the temperature of the solution. So they would feel hot, so to say. They would feel warm to the touch. Think of something like MREs. You mix water into the pouch, kind of shake it, stir it up, and you get an extremely amount of heat released. Okay, that's exothermic. Exothermic, think of exiting. Okay, an exiting of the heat. So you're going to see an increase in temperature. It's much like the ice melt on sidewalks and on the streets. When that dissolves and interacts with the snow and ice, there's an increase often in the temperature. That's an exothermic process. An endothermic process is one where heat is entering the system, okay, is entering, and when we put our hands on those beakers or test tubes, we're going to often feel a cooler, colder temperature. Okay, an example would be like what athletic trainers often carry in their first aid bags. They have those instant cold packs where you kind of crack an internal capsule and shake it up and it gets extremely cold very quickly. That's an endothermic measurement, heat of solution. Okay, we see a decrease in temperature. It's going to feel cold often. Okay, we're going to feel a cold temperature. And so think of endothermic as heat is entering the system. Exothermic, heat is exiting the system. And okay, so entrance and exit. Think of it in that nature. And okay, now one thing about gases. When you dissolve gases into a solution, it's going to be exothermic. Okay, that's going to be an exothermic process. And because the solute, meaning the gas molecules, they don't really have measurable intermolecular attractions because the molecules are so far apart and they're so high energy already. Okay. Now there's some examples of heats of solution there in your textbook on the table 13.5 if you want to reference them just to get some quantitative ideas of heats of solution. Okay, so let's move on to measuring the concentration of solutions. So how much solute is in the actual solution. Okay, so the concentration. Here are the 2 most common methods of concentration measurement. There's molarity and there's molality. Okay, and they're both symbolized with the letter M, but molarity will be a large capital M, whereas molality will be a lowercase m, and oftentimes you'll see it in textbooks. It's written kind of italicized with a curly m. Now the difference between them is molarity is measuring the moles of solute, so the substance that's dissolving, per liter of solution. So notice that is moles per liter. That's moles per volume, okay, measurement. Okay. Molality is measuring moles of solute. Same thing, but it's per kilogram of solvent, okay, per kilogram of solvent. And remember that 1 kilogram is equal to 1,000 grams. And another relationship you may want to remember is that with water, the standard density of water is 1 gram of water equals 1 milliliter of water. Okay, that's the density relationship. So if you were to have a 1,000 milliliters of water, which is 1 liter, that would be 1,000 grams or 1 kilogram of water. Okay, so let's walk through these two sample problems. We've got first, what volume of 3 molar sodium chloride is needed for a reaction that requires 146.3 grams of sodium chloride. So molarity equals moles of solute, moles of NaCl per liter of solution. Okay, molarity is 3.00. Okay, so that's 3 moles per 1 liter of solution, and we need 146.3 grams of sodium chloride. Well, we need to change that to moles, so let's do that. 146.3 grams of NaCl, and remember that we got to use molar mass, so 1 mole, and its molar mass, and I'll go ahead and calculate it for you. It's about 58.45 grams of sodium chloride. Okay. So let's convert that. So we have 146.3 divided by 58.45. So it looks like we have about 2.503 moles of NaCl. Okay, is what we are needing. So let's put that right here, 2.503 mole of NaCl. And we can then solve for the liters of solution, because that's what we don't know. But we know that our solution is 3 molar. And that means 3 moles for every liter of solution. Okay, so not bad so far. Okay, so let's solve this. Let's just rearrange, and we'll have 2.503 moles NaCl divided by 3 molar, and that's going to equal the liters of solution that we need. So divide this by 3, and it looks like we need 0.834 liters of solution. Okay, and if you want to put that into milliliters, that's just 834 milliliters. Okay, 834 milliliters. Okay, so molarity is just equal to moles per liter. Okay, now let's try this second one with molality. Okay, molality is equal to moles of solute, just like molarity, but per kilogram of solvent. So we have molality is equal to moles of solute per kilogram of solvent. And our example problem here is what quantity in grams of methanol, and here's the formula for methanol, is required to prepare 0.244 molal solution in 400 grams of water. Okay, well, first thing I notice is this 400 grams of water. Let's change that to kilograms, so 0.400 kilograms, because that's our solvent. Okay, and let's put that into place, 0.400. Okay, moles of ethanol, CH3OH, and the molality of this solution needs to be 0.244. Okay, so take these values and always write the formula and set it up. Don't try to do this in your head, and then also don't get frustrated. If you'll set the formula and put numbers into place, then you know exactly what the mathematical process here is. So moles of methanol is 0.244 times 0.4, so that comes out to be 0.0976. Okay. And they want us to change it to grams, so that's easy enough. We've been doing that all year, so 0.0976 moles of methanol. And we need to set up our conversion factor here, 1 mole of methanol, and we need the molar mass of that. So the molar mass of it, remember how we do that, we just take all of the molar masses, add those up, and we get somewhere around 32.04 roughly is our molar mass. About 32.04 grams is the molar mass. We solve this, okay, times 0.0976, and we get somewhere, let's see, 3 sig figs, so we got 3.13 grams of methanol is needed. Okay, 3.13 grams of methanol is needed. Okay. Now in the video playlist I have of solution determination, solution and concentration determination, there are, I believe, 4 videos that break down these concentration calculations in more detail. So you may want to take some time and go through those.